let's kind of get started. I've got one last topic to do in applications, and then I'll spend a little bit of time on your next topic, which is parametric equations. We'll talk about a change in plan pairs. And then after that, hopefully I'll have 5-10 minutes to talk about your midterm. So we have done power series, in particular Maclaurin series. And I'm going to give you a Maclaurin series already pre-done. My favorite Maclaurin series in the world, right? E to the x. It's such an elegant power series, isn't it? Now, we're going to use that power series to find other power series, but not doing it the f dashed, f double dashed, f triple dashed, and trying to find a pattern. You notice finding those patterns can be quite challenging and sometimes impossible. And certainly takes a lot of work. We are going to do a different technique. We are going to use substitution. So suppose I wanted to find the power series for e to the 2x. Wouldn't it be nice if I could use the power series for somebody I already know to get this one? And we've tried this trick before. Remember the 1 over 1 minus x and 1 over 1 plus x, and you could use it to get 1 over 1 minus x squared? Wasn't it all about substitution? So don't think of that as x anymore. Think of that as a placeholder. So if you want e to the 2x, don't you just stick 2x there? Substitution. And so the power series for e to the 2x would be that. Does that seem reasonable? And of course, we have a little style point issue when we do sigma. And the style point issue is that the x's have to be on their own. So it has to be x to the power of n, right? So you make it that. Now, suppose you were being asked to do x cubed e to the negative x. So suppose that was the function you wanted to find a power series for, right? X cubed e to the negative x. Well, the way you would approach that is you'd think of it as x cubed, and then you do a power series for e to the negative x. What substitution will I replace this x by to get the power series for e to the negative x? What will I replace this x by to get the power series for e to the power of negative x?
Just negative x.
Right. Think substitution. Now, there are going to be a little bit more style points in this question. And the first one is we're going to make sure that the powers of x's are separated. What do you think I'm going to do with that x cubed now? What do you think is going to happen to this x cubed? We've done that.
Add it.
Yeah, it's going to come inside. And wouldn't that just add 3 to the power? So do you see that you can use these power series as building blocks for power series of other functions? Can you imagine how much trouble it might be to do a power series of something like this from scratch? And how much easier it is just to use this trick instead. So far, so good. Right. Let's give you a new power series. That is the power series for the cosine of Hold on, let me do it. I'm trying to do it in my head here. There it is. It's just x to the 2n. That's the power series, say, for cosine x. If I want the power series for the cosine of 2x cubed, then I just replace the x by 2x cubed. Oh, by the way, let me rewrite this darn thing again. There we go. There's your power series. Right. If you want the power series for 2x cubed, you replace the x by 2x cubed. And then you do some still points on it. Two to the power of 2n. X cubed to the power of 2n. 2n factorial. Probably didn't need this line, but I'll put it in anyway. You're going to take 2, raise it to the power of 2n. You're going to take x cubed and raise it to the power of 2n. When you take x cubed and you raise it to the power of 2n, don't you get x to the 6n? Now, as I say, you should be able to go from there, but I wanted to just put that in just in case you were wondering, you know, what the heck went on, right? Power series for sine x. That's why I was kind of back to front in the other one. And there we go. The power series for the sine of 2x. And if I wanted to find say that guy, it would be x. And wouldn't I replace this guy with x squared? Agreed? This fella, x squared. So x squared raised to the power 2n plus 1. Raise this and you double everything, so you get 4n plus 2. And this guy, add it. There we go. If you add on to this fella, now when you look at this power series, which is the power series for x sine x squared, can you trust me if you try to do that the old-fashioned way, right? Find the derivative, find the second, third, and fourth derivative, evaluate them at 0, and then try and find a pattern. You'd be hard-pressed to figure out that, because a large percentage of these answers ends up being zeros. So you're going to get one of those 0, 0, 4, 0, 0, 16 over 3, 0, 0, 256 over 9, and you're going, what the heck are those numbers coming from? And how do I cope with all those zeros, right? So this is essentially a very useful technique. And aren't most functions built from basic building blocks? What do I mean by that? Aren't most functions got sines x's in it, e to the x's in it, you know, and things like that? Well, if you know what they're built from, can't you kind of put them together with power series and then just generate the power series that way? We're only doing the top of that. But there are techniques for taking one power series and multiplying it by another power series. In other words, you won't need to worry about this, but it is possible to find the power series of this guy and the power series of this guy. So imagine two ugly power series. And there is a way of multiplying them together. In fact, what you do is you create a double power series. A double power series has two sigmas in it. So it's a sigma of a sigma, which is a kind of hyper power series. But that's kind of advanced, and don't worry about it because you're not going to see it. You might never see it, actually. Depends on what branch of mathematics you go into. Any questions?
So just to confirm for the style points, when we had the 2 to the 2n, we always want to keep that as the smallest like possible number. Like we would never convert it to 4 to the n. On the left page.
This one?
Yeah, just where it's the 2 to the 2n. Just for style points, we would keep it as 2 and we wouldn't change it to 4 to the n, for instance.
Oh, I was looking at this. Correct.
Okay.
Right. But if you ever got a 4 to the 2n, different question, right? I'd be quite happy with that and I wouldn't argue about it, but some people might call it that. And it's correct, and I wouldn't fault you for either version, so it doesn't matter.
Okay, thanks.
That's kind of a nice direction, so I would leave it alone. Are we good? Any other questions? Then it's time for us to look at our next section. And our next section, if I can close this off, is parametric equations. Chapter. It's a very small chapter. It's going to get even smaller. It's only got 2 sections in it, and we're basically looking at parametric equations and curves. And I am going to nip over. So while I'm doing this, why don't you just put your last name down for attendance? Because I might be hitting some buttons for a while till I get what I need. Okay. Okay. We got it, I think. We got it. No, I didn't. Go and have a coffee or something. This is taking longer than I thought. I had this darn thing somewhere, and now I can't find it. I know what I do. I'll go into my Calc 4 class because they have it. Do they have it? Done. Okay. Let's just find it from scratch then. What all this is doing, I'm trying to find a piece of software that draws parametric curves. For some reason, I can't find one. I can do it. Okay, we got it. You know, if you ever become a teacher, don't do what I just do. Be prepared. don't think you've got something and then suddenly find out it's not there. That's not a good idea. I'm just setting up one now. And I'll say if this doesn't work, then I'll figure it out. Right. That looks good. Right. So parametric curves then. Parametric curve takes this format. You describe the x and y coordinate of the point on the curve by giving x and y in terms of another function or functions using t. And then you can have t start and finish at any number you like. So an example of a parametric curve might be x is sine t, and that y is t, and that t starts at 0 and maybe finishes at 6 pi. Okay. So when you type that one, oh, let me show you where that guy is. It's in Desmos. Here it is. Right. So set this little guy up. That was just a little practice. Right. So you type in the x guy, which is sine of t, and then you type in the y guy, which in my case I just made it a simple t, and there you go. And from 0 to, what did I say, 6 pi. And that's called a parametric curve. Now you can make this a little bit more interesting. You could go, I don't know, that's t squared. And then put a cosine in front of it. That should be interesting. Oh, look at that guy. Oh, come on, that is pretty ugly. But I mean, look at it, right? Now, maybe I should be more restrictive. There. And if I stick a bit of symmetry in it, there. It would be downright impossible for me to create a curve like that using y equals a function of x. Would you agree? If we made one, you just couldn't make it happen. Certain things just are elegant or are only doable using x as a function of t, y as a function of t. You use parametric equations. If I reduce this guy down to just sine t over cosine t, isn't that a very elegant way of drawing a circle? But you can do things like that. And that. And only make half a circle. And if I play about with the range of t's, couldn't I make it the top half of the circle, the left hand of the circle? In fact, couldn't I even do it for 3/4 of a circle? And isn't that also impossible to do as a y equals f of x? Right? It's not really easy to do. So parametric equations are typically a niche market for unusual curves. And how do you draw them? And you know, Desmos is great. And the trick, bracket, bracket. Okay. Remember to do little curve brackets and you're fine. Let's see if I can make something. I don't know what I'm going to make here because I'm just doing it as I kind of think of it. X could be t, and then y could be t squared. And essentially, haven't I just drawn, well, eventually you'll see it, a piece of a quadratic curve. So if you want to sketch any quadratic, won't you just go to Desmos and put a little bracket around it like this and see what it looks like? So far, so good. So what are the kinds of things you're going to be asked to do? Let me bring this up. Okay. Probably easier to do this on paper to show you the kinds of things. Suppose I give you a parametric curve. X is equal to 9t squared plus 9t, and that y is 3 to the power of t plus 1. And for various values of t, let's pick this one, you can find the coordinates. So let's suppose t equals 1. The x coordinate will be 9 plus 9, which is 18, and the y coordinate will be 3 to the power of 2, which is 9. Let's pick 0. The x coordinate is 0, and that's 3. Let's pick -1. That'll be 1. That's basically -9, so that's 9. Take away 9, that's 0, and so on and so on, right? Then what I could do, this would be old school. Couldn't I just plot at 0, 1, which would that be? 0, 1. And then at 0, 3, and then at 18, 9. If I did enough points, couldn't I just draw what the damn thing looked like? In the olden days, i.e. when I was at school, there was no such thing as Desmos. So when we had to draw parametric curves, we basically had to do little snapshots, 8, 9, 10, boringest job in the world, right? Find 8, 9, 10 coordinates, isn't it? Join the dots. Now, there's one thing that parametric curves, when you sketch them, that none of the other kinds of curves that you do have. If you imagine that's my parametric curve, and this is the number you got when t is 0, and let's say that's the number you got when t is 3, a parametric curve has a direction. You travel from 0 to 3. The fact that they use this dummy variable, that's what they call t, they use this dummy variable t isn't a coincidence. It's because it very often represents time. Because one of the good things about parametric is not only can it do weird curves, can't it also have those curves in the idea that you're traveling along them, and at time equals 3, this is where you are, and at t equals 5, this is where you are. And that is a very useful concept. Can you think that you're trying to model some zigzag boat on the water? Wouldn't it be very interesting or very helpful to know where it would be at any given time? Because sometimes it speeds up, right? And sometimes it slows down. So if I had a parametric curve and it looked, let's say, like this, if I put in a dot at each second, meaning t equals 1, t equals 2, t equals 3, 4, 5, 6, 7. Don't you also get an idea of how fast or how slow it's traveling along that curve, right? Can you see in the first second, quite a lot, slowing down, speeding up. Can you see that feeling? So parametric curves don't just represent shapes or weird curves. Can they also be used to represent journeys, things traveling along a certain pathway? And you do get extra information of it was traveling that way. And if you plot enough of these little dots, can't you also get an impression of how quickly or how slowly it is at any given part of that journey? In fact, it could happen. Suppose that was t equals 10, t equals 11, and t equals 12. What would that be telling me about the journey of this object? What was it doing in those 2 seconds?
It stopped completely.
Yeah. So you could even have an object that travels, speeds up, slows down, stops for a few seconds, then keeps traveling again, right? That's pretty versatile, isn't it? Parametric allows you to model moving objects. It's one of its big uses. Now, you're going to get questions which basically boil down to, here is a parametric equation. Here is the range of t's that it was being used for. And they give you 4 pictures. Won't you go straight to Desmos and essentially type in this? And then in that little T thing down here, won't you do that? And you'll have your picture. And won't you look at your picture and look at their 4 and pick the one that looks like it? Isn't that going to be a very easy question to do now that Desmos is around? But it is fun. You get to see lots of ones. So I'm scanning through. Yep, that's pretty much all these questions here. Yeah, that's still the same basic one. Right. And now the last kind of question. And this is the last thing I want to do today as far as work is concerned. Oops. How to convert from parametric to Cartesian. So parametric means the x's and the y's are functions of t, and Cartesian means, you know, things like x, y squared equals xy, right? Things that use x's and y's. So let's suppose I tell you that x is t squared plus 1, and that y is 2t minus 1. So the technique that you're going to use to change this parametric into Cartesian depends on the information, because there are different techniques for different situations, algebraic situations. One of the most common techniques we're going to use is reference substitution. So what you do is you look at the 2 equations and you say to yourself, which one of those 2 equations would be the easiest and simplest looking if I solved it for t? In other words, I rewrote it as t equals. So which one of those 2 would be the simplest to deal with? And look,
X seems like it would be the easiest.
Right, well, let's show you what that would look like. So you do x minus 1 is t squared. Great. Now, how would you get t? You take the square root of both sides. And you'd have to put a plus minus in, wouldn't you? Because when you take a square root, you could get a positive or a negative.
Good point.
But you'll learn. I mean, that's how you do things. You try it out. So let's try this one. If I add 1 to both sides, and then I basically divide everybody by 2, it's going to be ugly no matter what I do, isn't it? How about y plus 1 over 2 now I've thought about it? Then you can go here and you can substitute the t equals y plus 1 over 2, right, into equation 1. And so you get x equals y plus 1 over 2 squared plus 1. Would you agree that I now have, it's called an implicit equation. Don't I have a Cartesian answer, right? Agreed everything is in X's and Y's. Do you think we would expect you just to leave it that way, or do you think we should do some style points? What do you think you should do here? I know you want to leave it, but that's not allowed. So what do you do?
You can square the top and bottom.
Okay, and if you do that, you get y squared plus, whoops, 2y plus 1 over 4. That works. Me personally, I don't like fractions, so I'll multiply everybody by 4. And that's looking pretty good, isn't it? No fractions anymore. I guess that's correct, but I would probably rewrite it slightly differently. 4x, take away y squared, take away 2y equals 5. There is a convention that you try and write all the variables on one side equals a number. Examples of that, don't you typically write circles like that? And circles would be an example. So one of them is substitution. Now let me return back to the first attempt, that one. If we used that attempt then, wouldn't y be 2 lots of plus or minus the square root of x minus 1, take away 1? Would you agree that that's a little bit clunky? But technically speaking, isn't it also correct? Agreed? When you look at the two, would you also agree that this one here is just, I don't know how to phrase it, it's just right? Will you agree? That's just, now let's keep away from plus minuses. We typically don't like that. How about this one? And this one's got an interesting little problem to it, which I kind of like. Which one of those two do you think would be the simplest and nicest to turn into a t equals? Number 1 or number 2?
Number 2 is y plus 1 equals t.
Agreed. And that means x is equal to e
to the power of y
plus
plus
1.
2.
Yeah. And would you agree that is a very pretty, weird looking, but fine, right?
Yeah.
Yeah. Now, just, I wouldn't do this, but just to show you, it's possible to do the other one. If you took the natural log of both sides, and then you take 1 away, don't you get t? And then won't this one become y equals the natural log of x, take away 1, take away 1, and you get y equals the natural log of x, take away 2. Which is a little bit annoying, because doesn't that mean there's 2 correct answers? Would you believe that this is totally equivalent to that? Because they are the same curve. And they don't look very much like each other, would you agree? But they are. So that, and this is WebAssign's problem, not ours. WebAssign may only know the top answer. But this bottom answer, in my opinion, is totally cool. Would you agree that's, in some ways, isn't that even prettier than that one? Right. So you may end up getting the wrong one of the two when you do WebAssign. If you think that you've got the right one, you can just tell me and I'll have a look, and if it's right, I'll just give you the points. Or you can just say, oh, heck, I'll do it the other one just to keep them happy and get that one. Right. Now, the last situation is, what do you do when the trig involved? Oops, let me do that again. Didn't mean that. Substitution is not going to work here. This one is kind of on its own. None of the others are going to look like this. So whenever you see a sine and a cosine, you're going to tackle it this way. I'm going to take equation 1 and add 1 to both sides. I'm going to take equation 2 and subtract 1 from both sides. And they're going to be my new equation 1s and equation 2s. I'm going to take equation 1 and divide it by 2. That's my new equation 1. And equation 2 and divide it by 3. And that's my new 2 equations. Any ideas what I'm going to do next?
Are you going to like square both of them and add them together because that'll be equal to 1?
Nailed it. And so we get x plus 1 over 2 squared plus y minus 1 over 3 squared is equal to those two added, which is 1. And then just to make it look pretty, and if you're interested, that is an ellipse centered at -1, 1 with a x-axis of 2 units and a vertical axis of 3. Now, would you agree that's different from the substitution method? So in substitution method, you pick one of the 2 equations that you think you can turn into a t equals. It's pretty nice and easy to deal with. And then once you got it, you plug it into the other one, you're done. In this one, isn't it a trig identity, sine squared plus cos squared? And you might also want to do a secant squared minus tan squared, which is another identity that gives you 1 as well. Are we good? Right, changing plans. Chapter 10 is not in the homework. I'll be removing it from my list as soon as I finish this. And it's not in the midterm. And it will appear in the following week's work, right? But we've got a good head start on it, right? So we should be able to get through it pretty quickly. Next piece of information is I'll be taking my personal day off on Tuesday. So you lot are going to be getting a free day. So that'll give you a day to recover from your midterm. I'm just closing off some windows here and getting back into our thing. And one last tell you what's, the way things are going to work. So on, it is good. Right, so there we go. You should be looking at Canvas. Agreed? Right. There's a link to the Zoom meeting. It is not our class Zoom meeting. It's a different Zoom meeting link. You click on this guy. All right. Hit that fella. Make it a bit bigger. We know it's on Monday. I've said that enough times, so don't turn up on Monday and say what midterm. That will not be a good sentence. It's going to be on the 5 weeks, and that means it's now only, that's a great phrase, chapter 11, right? So it's kind of clean, right? Sequences and series. First stuff you're going to see is on sequences, that's week 1 work. Last thing you're going to see is like we just did today, Maclaurin's Taylor series stuff, right? There are going to be 10 multiple choice questions and then 10 full questions. So the multiple choice questions I do not want to see working, right? It might be, here is a sequence, and ask you something about it. Does it converge? Does it absolutely converge? Whatever it might be. Say A, B, C, D, you pick the right one. So all you do is you tell me the answer. When you do multiple choice question, if it's taking you more than 3 minutes to do it, you're doing it wrong. So pick C. They should be shortcuts or tricks, or just, hopefully, have a lot of you got to the point where a lot of sequences, you can just look at them and you know they're going to converge, for example. Well, if you know that, isn't that question going to be really quick? If that was the question, does it converge? There are 2 time slots, 8 till 10, 9 till 11, right? You'll turn up with your camera on so I can see you and you don't cheat. And it will be called midterm exam. Now let me leave this fella and go back to here. See this midterm practice exam with solutions? That will disappear. And probably you will then see the real midterm there, right? And when you click on it, there's going to be a PDF there. And it'll look just like that guy, right? And you will do your answers on paper. Oh, shooting space, I didn't disclose that, did I? I did, didn't I? Oops. Give me a second while I load it all back up again. Oh, good, it was quick. So that's going to be there. Now, you're going to have to upload your work, right? You've written your work down, right? I want to see as much as possible. I give partial credit. So if you do it the right method, but a plus turns into a minus and you get the wrong answer, not a biggie. You won't lose much if I see the working. So you need to upload it. One way of doing it is a program called Microsoft Lens. A lot of you have got other things, I've been told, cam scanner, maybe even use your printer scanner. But whatever it is, you got to upload it. If you're doing Microsoft Lens, click on this guy. You can upload the Android here and the Apple here. Tell me if these links are live. I believe they are, but if they change them, I can find where the new link is. And if you click on this little video, if you've never uploaded work using Cam Scanner before, there you go. It tells you how to do it. And it tells you a lot more than you need, but it tells you what you do need as well. Going back. Now, you want to practice at doing it. There's a little dummy one. Essentially, you just go like that, and you click on this. And if you've saved it on OneDrive, it's here. If you've got it on your phone and you use your phone to get into Canvas, it's here. You just choose a file, pick the PDF that you want, open it up, right? And then submit, and that's it. It's as quick as that. So once you've got your working in the form of a PDF, you can just upload it. Well, evidently I picked a really big file, but nonetheless it's there. I hope I didn't pick up my tax return. That wouldn't be a good file to have there. Oh no, I uploaded a PDF of a textbook, which is pretty big, so I'm not surprised. I'm not going to click on that, it would open up. But you can overwrite it, right? Suppose you do it and then you realize that you forgot page 3, oh God, they were 2 stuck together. Just redo it again, right? Take pictures of them all, hit new attempt, go over here, choose file, and then choose, let's do a letter of recommendation, and hit that. Submit assignment. That should be a lot quicker, which it is. So if you miss a page or something, now when you're finished uploading, don't leave the Zoom meeting. Tell me that you've done it. I go in and I check. And if I can see it and I can read it, it's good. Now, the reason I do that is for 90% of you, it works perfectly, but it's just a backup. But for 1 in 10 of you, so that's like 2 in this class, it's going to be so faint I can't read it. Or it never uploaded properly. It's got ziggy zag squiggles or something on it. And then I'll say, it didn't work. Do you want to do it again? Right, because we don't want you under the impression that everything's fine. And then I shoot an email saying to you panically, I can't see your midterm. Right? That's like you doing it in class, right? And taking your midterm home with you. And then I phone you and say, where's your midterm? And you say, oh, I've got it here, because don't I have the problem of, well, she's had 3 or 4 hours to fix them all. And then she's going to show me the fixed version. You see the problem with that? So I need to make sure that when you upload it to me, that's it, right? That's the ultimate version. Nothing else can change because it's there. And I think that's everything. And 9:50. How about that for timing? Any questions before we go? Anything that you're not clear about?
So is everything going to be on paper, like even the multiple choice answers on the paper?
Yeah, so when you put the paper, all you do with multiple choice, Jade, is say 1, it was C, 2, D, 3, E, 4, I don't know. No, you don't do 4, I don't know. If you don't know, Kira, you put C, right? Or B, or whatever your lucky letter of the alphabet is. And that's all I would see for the multiple choice. And section 2, I'd see all the working. For some of you, it might be helpful if you do a little trick that I found helpful, at least. Have a quick look through section 2, and the ones you know how to do really well, do them first. And you can do them in separate pieces of paper, right? Question 4 on a piece of paper, question 3, and then you're finished. Can't you just put them in order and photocopy it to me? Get it to me. The reason I say you do that is, there's going to be at least 1 or 2 stinkers, ones that you just don't get right, or you're going to have problems with. Best to keep them at the end, because you'll be psychologically much happier if you've already done 7 good questions, right? And you come to question 8, aren't you going to be in the right frame of mind? Especially if the horrible question ends up being question 2. Right, because you could spend forever in a day on it, and then you get that, oh God, I've still 8 questions and I've only 30 minutes left, and panic, right? So we want to avoid that situation. So do all the easy ones first, and then do the hard ones last.
Are we allowed to join either meeting? Do we just
Yeah.
get to choose? Okay, cool.
You could join halfway through both of them if you wanted, as long as when you start and finish is a 2-hour slot, right?
Awesome.
Anything else?
Are we allowed to use Desmos?
I will make sure Desmos is in that little module. I thought it was, and then I couldn't find it, but it will be there. And if it's not, you will say it's not there, and I will go and I'll put it in it, right? So it will be there. You're allowed to use any physical written notes. You are not allowed to use Mathematica or math solving equation programs or anything that's basically cheating, right? So it's your brain and anything you've written down on a piece of paper to help your brain. And that's all. So no phoning a friend, right?
Are we allowed to use like digital notes at all? I just have all my notes on a digital notebook. I have them in a printable format if they need to be physical though.
Are you using that at the same time you're going to be doing Zoom?
No, it would be on a different device.
And you're fine. So that's kind of electronic version of it.
It's just a notebook. It's just notes.
That's cool. You'll have to send me your notes. Are they any good?
Oh, they're fabulous. Yeah, there's an index with links on it. Yeah.
Oh, I'm not joking there. If you don't mind, if you want to at least.
Totally. Yeah, I'll send notes.
Would you think your notes might be helpful for other people?
Oh yeah. Yeah, I try and make them so they're really comprehensive.
if Kira sends us the notes, I will put them on that same module, and so that you can use them over the weekend. And every little bit helps. Thank you, Kira. You should all be saying thank you to Kira. And when you meet her, give her some money. No, she doesn't want money. Well,
I'll
if you
take coffee. You can bring me coffee.
me the money instead, then how about that?
Yeah, do that.
I'm going to hang about for any questions if there are.